Now we had seen the two phases. One is the instruction fetch. Oh, I think we have seen only one phase, right? Instruction fetch, which has taken 2 cycles. And now we are going to decode the instruction. So every instruction in order to fetch has taken up T0 and T1. So T0 and T1 are for fetch. Now what is remaining? Next one is T2. So after every clock, the timing signal will be incremented by 1. It will start from T0 and it will continuously be incremented after every clock unless you make that clear input to 1. If the instruction execution is over completely, then we are going to clear that sequence counter, and so we enter T0. Until we do that, it will continuously be incremented. Therefore, now an instruction is fetched and the instruction is present in the instruction register, and at T2 we are going to decode it. So how are we going to decode it is, we now know that instruction is present in IR. Got it? Therefore, we go to IR instruction register, and you can look at the instruction register. It will be like this. You see the instruction register, I told you that till from 0, 1, so on till 11, this entire thing is operand, right? And then 12, 13, 14, 15, and this bit is I, which is nothing but the mode, addressing mode, and these 3 bits are opcode. Got it? So now into the decoder we have to send these 3 bits, right? Therefore, at this point at T2 I'll be activating the decoder, and I'll send to the decoder these 3 bits, 14, 13 and 12. These 3 bits I'll send to the decoder, and decoder is going to give us output signals, right? So what kind of decoder is it? It is a 3/8 decoder, right? Therefore, the output is going to be either D1 or D2 or so on till D7. So any one of these is going to be 1 depending on what this is, and depending on the type of this, we can know which one is it, which instruction is that is decode. Along with that, this particular thing, so this operand can be either the direct address of the operand or indirect address of the operand. That depends on what this one is. Anyway, we have to go to the memory and get that operand, isn't it? Either we have to go to the memory and get the address of the operand or get the operand itself. So since we have to go to the memory, we have to move these 12 bits, the least significant 12 bits, into our register. So which register? Address register. Therefore, into the address register I am going to send 0 to 11 bits. The least significant 12 bits are going to be passed into the address register, again through the bus only. You know what, when you select this IR, everything, all these 16 bits will be placed onto the bus, but then since address register is just 12 bit, it will read the least significant 12 bits and it will ignore the remaining bits. Therefore, by doing this, what we are trying to send is actual address, only address part, and we are going to have a special flag. Assume that it is I, and into this special flag, in the same cycle, I'm going to in the same clock cycle I'm going to send IR of 15. This part will be sent there. So by doing this, decoding will be complete. How? The decoder will be enabled at the same point. So for the decoder we have enable signal, right? And now to the enable signal I am going to give T2. Got it? Therefore, this is already connected like that. Decoder is connected already to the instruction register, so passing it is straight away, but then we are going to enable it here, and one of the outputs from D0 to D7 is going to be activated because of this. And after that, along with that, I have to even move this IR to A. So what I do is, I'll select this IR register. I don't remember the exact number of IR. I think the number is 4, I guess. So 4 means 100. If the number is 4, then to the bus circuit I have to enable 100, which means S2, S1, S0 are there, right? So to S1 I have to give this part T2 as input. One of the input to S2 has to be T1, and then the remaining will be 0 anyway because of this. Therefore, what will be selected? This entire IR will be selected, and that will be placed on the bus, right? And now that bus is also connected to all the resistors. Along with that resistors, all the resistors, one of the resistor is nothing but AR, right? How can I load AR? To the load input I am going to connect this particular T2. Got it? And similarly, anyway this bit will be directly connected to I, the flip-flop I, and to that flip-flop load input of the flip-flop I'll give T2, right? If this is T2, I'll give T2. Therefore T2 signal will be given to all the places appropriately, so that these three operations, micro operations, will take place. So what are the three micro operations? Decoder is enabled, and before enabling, the required register is already filled with the instruction. Therefore we can know exactly what type of instruction it is, and also the address part of the operation is directly sent to address register. So in case if it is a memory reference operator instruction, memory will be referred in the next cycle, not now. And also I is saved. Got it? And now you have to understand what type of instruction it is depending on what happens here. Depending on the output of this decoder, you have to understand what type of operation it is. So if you see this, since we are using only 3 bits, it might look as if we have only 7 or 8 different types of instructions, but then it is false. The reason is, I am not always going to have this operand field as valid. Operand field will be valid only when there is memory reference. Otherwise, if it is a register reference instruction, I need not use this. In that case, I can increase the number of instructions. Got it? So see this. What are the different types of instructions is, depending on these 3 bits, we have various types of instructions. For D0 till D7, D6, all these instructions are memory reference. So memory reference means the second part is going to be an operand, right? Operand address, either direct or indirect. In case if D7 is present, then the instructions can be either register reference instructions, or they can be IO related instructions, right? And how can we decide which one it is? We can decide by seeing the I bit. If I is 0, they are register reference instructions. If I is 1, they are IO related instructions. Are you understanding this? So what type of instruction it is, how can we decide is by looking at this decoder outputs. If it is D0 to D6, they are all memory related instructions. You can look at this. They are all memory related instructions. This part, the first part I have written here, is all memory related instructions. The first part. Okay. In case if it is D7 and I is 0, then it is register related instructions, which means the second part. This is register related instructions. In case if I is 1, it is IO related instructions, which means the third part, right? Therefore, in our case, we have divided the type of instruction into 3 types. One is memory related, other is only register related, and the other is IO related. Now how did I distinguish them? From D0 to D6, if you see any of them highlighted of this one, if you get 1 in any of these places, then it is memory related. And how can you relate these two? If D7 equal to 1, in this case any of them can be 1. In this case, if D7 equal to 1 and if I equal to 0, the most significant bit, if it is equal to 0, then we are going to call it as register reference instruction, right? and if D7 equal to 1 and if I equal to 1, we are going to think that it is IO related instruction. So overall we are having 25 instructions. Now along with the instruction here, along with each instruction, I have also given the hexadecimal code associated with that. We know that every instruction is a 16-bit instruction here, therefore we should have 16 bits. Now I am converting these 16 bits into this 444 bits each, and I converted each 4 bit into a hexadecimal number. So that is how I have given the hexadecimal numbers here, right? So if you watch it, let's see here. So if you watch it, the first one, look at the AND instruction. It is given as 0xxx. What is the meaning of this one is, the first 4 bits are all zeros, 0 0 0 0, and the next one is don't care. All the 4 bits are don't care, all the 4 bits are don't care, which means all the 12 bits are don't cares. Now if you see this, these 3 parts actually form D0, isn't it? And this part says that it is a direct address, right? Not indirect, it is direct address. So what does it mean? This instruction actually means add the memory word to the accumulator. Already accumulator will be loaded with something. Now some address is given here. This X part is nothing but the address of the operand. Go to the memory, get the operand from that address and AND it, sorry it is not adding, and AND it with the accumulator and store the result to the accumulator. Got it? And in case if I equal to 0, it is all about it, and in case if I equal to 1, it is all about it, which means all these memory reference operands or all the memory related instructions are actually having 2 variants. One variant is using direct addressing and the other variant is using indirect addressing. Now if you look at 8xxx, 8xxx is nothing but, if you see 8, right? So 8xxx means the first 4 bits are 1 0 0 0 and the remaining 12 bits are don't care. Now if you see this one denotes D0. So I told you that D0 to D7, so D0 to D6, it is all memory related instruction. Therefore it is memory related instruction, and I says that it is indirect, which means whatever is present here, it is not the effective address. You have to go into this memory location to get the effective address. Got it? So the way you handle this one, this instruction and this instruction, even though the operation is same, the way you get the operand is going to be different, which means in this case effective address is directly given and our address register directly gets the effective address. See this, while decoding itself I am trying to send into address register whatever is present in the address part of the instruction. Therefore if the instruction is containing the direct address, then address register in this case is directly going to get the effective address. But if the instruction is going to contain indirect address, then address register will get the address of the address, isn't it? And therefore you have to go to the memory and get that address, then only you are going to get the effective address. So whenever I equal to 0, you can directly go and fetch the operand from the memory. Whenever I equal to 1, you have to go and fetch the address of the operand first, and then operand has to be fetched. Therefore compared to these instructions with I equal to 0 will execute faster, or at least 1 clock cycle faster, assuming that the memory read will take 1 clock. In case if memory read takes 1 clock, what happens is this one needs only 1 memory read operation to get the operand, but this one will need 2 memory read operations to get the operand. Therefore definitely these instructions will get delayed by 1 clock. Are you getting this? Okay, exactly where it get delayed, we'll see again the implementation. For now understand how these numbers are given, right? So these are the numbers in binary. When you type these numbers in binary, you are going to actually write the program. If you have to write the program, you have to type all these numbers manually, then you are going to do it. If you don't want to do it, then assembler is going to do it. Now what about the assembler? To the assembler you are going to give these mnemonics. Now these mnemonics will be automatically converted to these numbers What about compiler? Compiler will take the high level language and convert to these mnemonics first, and now the assembler will take these mnemonics and convert these numbers. Earlier, when there was no assembler and there was no compiler, people used to type the program in binary, which means they used to give these numbers as a program and the program is to get executed, right? Just think about the complexity. I'm trying to design the simplest computer. Probably this must be the computer used in 1980s, only with very few instructions and all, but still it might look very complex to you. Since it is beginning, it will look complex. Slowly it will be easy. Okay, watch it now. Now the next one is, this add is nothing but we are going to take a word which is present in the memory, whose address is given either by this or this address. This x will represent the address. I don't care what address it is. Okay, and then get that operand, add it to the accumulator and put the result in the accumulator. LDA means load the accumulator with the memory word specified here or here for it. Now if you watch it, 2xxs means it is 0010, right? And then all the remaining is don't care. And AXXS means 1010. So this one is going to represent D2, this one is going to represent D2, and this one is going to represent direct and indirect. Alright. And here STA means whatever is present in the accumulator, you have to store it to the memory. So how can you do that? You have to, in the bus, you have to select the accumulator, and then you have to enable the write input of the memory at the same time, right? You have to move this accumulator onto the bus and at the same time enable write input of the write to the memory, and then you have to put the address, and that address will be given in these 12 bits. Got it? So we shall get into the execution later. I'll take it later separately. Now 3xxs means it is 0011 is 3 and xx means 12 bits. And what about bxxx? It is nothing but 1011. So therefore, anyway, for both the instructions, this instruction type, so it is going to be D3. So D3 is going to be enabled, and I told you that D0 to D6 is memory reference, and this bit is going to say direct or indirect. And here also it is branch unconditional. BUN means branch unconditional, and 4xxx means it is 0100, right? So it is going to enable D4, and this 0 means it is indirect. And similarly CXXX means 1100, which means again D4 and indirect. BSA means branch and save instruction. It is a very important instruction when you are talking about function calls. If you have to implement a function call, we are going to use branch and save address. So it means that you save the address, return address at some point, and then you go to the branch, and at the end of that subroutine you are going to fetch the address which you have saved, that written address, and you are going to continue the execution. So branch and save address means if you are like this, if you are going in a flow and if you have to execute some other function, as before going there you save this written address somewhere. Let us say it is generally saved at some fixed address. So let us say in this case we are saving it at 0th location of the memory. Okay, and you save it and then you branch, and after this there will be return. So this return is going to take this one, take the address from 0 location and load it to PC, and it is going to contain. That is why branch and return address, branch and save address is used. Later we shall see again the execution and implementation clearly, but now see this one. So 5xxx means 0101, right, which means D5 will be enabled here, and 0 means indirect, and then D means 1101, right? So this is again D5, and 1 means indirect. And the next one is increment and skip if 0. So what it means is you have to fetch a word from the memory, increment it, and after incrementing it, if it is 0, we have to skip the next instruction. This means that increment and skip if 0, some address is provided along with the instruction. This is a memory reference, right? So it means that you have to fetch the operand which is present at the given address. Either directly address is given or indirectly it is given. whatever it is, you are supposed to fetch the operand and increment it. And in case after incrementing, if it happens to be 0, then you are supposed to skip the next instruction. How can you skip the next instruction? By incrementing program counter, right? We again will see the execution later, okay, implementation. Now it is showing 6, so 6 means 0 1 0 0 and all the 12 bits. These 12 bits are going to give us the operand, and this 6 is nothing but this 100 will give us D6, and I told you that from D0 to D6 we are having memory reference operations, right? And the 0 means direct, and 1 means indirect, and next one is A means 1100. So this is giving us D6, and this one is giving us that it is indirect. Got it? So this is increment and skip. So if you watch it, all these instructions are having in these 3 bits, they are having either 0 or 1 or 2 or 6, which means from 0 to 6 they are having some number. In case if these 3 bits happens to be 1, then the instruction can be either IO or the register related. So what do I mean by register related is, we need not go to the memory at all. We can directly we have to directly manipulate a register. So in that case, what happens is, your instruction part, even though it is containing the operand, this is invalid. You can use this part for some other purpose, right? And in this case we are using it to find out the type of instruction. So see this, I'll just explain you what it means now. So what I mean to say is, let's talk about register reference instructions. I just told you that instructions are of 3 types. One is memory related. In memory related, I told you that in the opcode, these 3 bits can be 000 to 110, which means from 0 to 6, and this bit can be either 0 or 1. Therefore, if this bit is going to be 0, then what is that we are going to get? From 0 to 6. That is why if you see this, from 0 to 6 we got it, right? And if this particular bit is going to be 1, what do we get? From 8 to A, right? So from 8 to A, isn't it? I think this is ABCDE, right? This must be E, I guess, right? Yeah. So last one is 1110, therefore this must be E, from 8 to E. So by looking at the first hexadecimal digit, you can identify whether it is which type of instruction it is, right? So if it happens to be from 0 to 6 or from 8 to E, you can think that it is a memory related instruction. Now the next one is register related instructions. For the register related instructions, I told you that we are going to have, I'm just talking about the opcode part. So this bit, this I bit is going to be 0, and this particular 3 bits of the opcode is going to be D7, which means 111. Therefore all the register related instructions will have 7 in the beginning. You can check this. These are all register related instructions and they will all have 7 in the beginning, right? And now this part will be useful or helpful in identifying that yes, this is a register related instruction. But then what type of instruction you have to perform, or what type of operation you should perform, that depends on the remaining bits, right? So how many bits are remaining? 12 bits are remaining, right? So let me number them: 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Now see this. Now first one is CLA. CLA means clear accumulator. So it is a register related information because accumulator is a register, right? So CL means clear. So whatever is present in accumulator, you have to make it as all zeros, right? So for that, what is that they are using? 7 8. 7 8 means this particular 1, this particular 11th bit is 1 and all are zeros. If you put all as zeros, it is going to be 7 followed by 8 followed by 0 0. 7800 is going to be CLA. And next one is CLE. CLE is nothing but clear that extra bit. Oh, I forgot to mention you about this extra bit. While there was an earlier diagram, there was adder and logic unit. When I was discussing about the bus, I have shown you some adder and logic unit. In that diagram, I have even shown you some flag with E, right? So this E is nothing but carry. Generally it is a carry, but in this case let's call it as the extra bit E. Okay, so now when I say CLE, it is nothing but clear this extra bit E. In normal sense, it is nothing but clear the carry. So for this 7400 is used. 7 means this one, 4 means this one is 0 and this one is 1 and all are zeros, got it? And next one is CMA. Are you understanding this? In case of memory related instructions, we are not able to use this part because we have to provide some operand here. That is why we are showing the type of instruction using these 3 bits, right? Now in case of other instructions, which means especially in case of register and IO, I need not provide any address because only registers are used, and the type of register can also be given even 1 bit. That is why instead of providing the address, I am using that part in order to specify the type of the instruction. That is why the number of instructions are not just 16 or 8. We have multiplied it. See, using 3 bits, we are typically supposed to get only 8 types of instructions, isn't it? But since we are allowed to use this part, I am able to get more instructions, and moreover, for this part, even decoder is also not required. When is decoder required? Whenever you are trying to store large information in small part, which means in 3 bits you are saving 8 parts, then only decoder is used to decode it. But in this case, 1 bit is used for each type of instruction. Therefore, decoder is not required. You can directly see this bit and say that, oh, this is CLA. You can see this and say that this is CLE. You need not even use a decoder. Got it? So in some sense, you can think of it as horizontal encoding, which means we are putting, for every bit we are giving one type of operation. Okay, forget about it. I don't want to confuse you now. Let's go slowly. Now try to understand this one, CMA. I'll get back, don't worry, I'll explain you everything. So even if you don't understand anything now, just keep watching, it will be very clear. Okay, and now the next instruction is CMA. So CMA means it is an operation related to accumulator only. I forgot what is CMA. Okay, I'll just refer to it and I'll get back to you. CMA means, one second. Complement. CMA means complement accumulator. For this it is using 7200. So 7200 means 7 is 0111 and 2 means 0010, right? So see this, 11th bit is used first, next 10th bit is used, next 9th bit is used, like this, 11 10 9, like this, one by one they are using. And CME means complement the extra bit. So it is using 7100. 71 means 0001, right? So that is why it is 1. So in this case it is 8, it is 4, it is 2, it is 1. 7100 complement the extra bit. And CIR means circular right, which means circular shift right. And CIL means circular shift left. And if you see this, 7080 is used. So 7080 means all these are zeros and this one is made 1 and all the remaining are zeros. And circular left means 7040 is used, which means all these are zeros and this one is 1, so 4. And the next one is INC. INC is increment the accumulator. So for that 7020 is used, so which means all these are zeros, and the next one, this particular one is 1. Got it? So let me show you here. So this particular one is 1, then what happens, 7 all zeros, that is by 0, and this one is 2 0, 7020, and next one is SPA. So SPA means skip if accumulator is positive. You test the sign of the data present in the accumulator, which is nothing but the most significant bit, and if it is positive, which means if the most significant bit of accumulator is 0, then you have to skip the next instruction. And it is very useful while you are testing some conditions, like if condition, if you want to implement. We shall get to an example there, but for now understand that it will test the sign of the accumulator, and if the number present in the accumulator is a positive number, it will not execute the next instruction, it will skip on to the next instruction by incrementing the program counter. Got it? Now it is 7010. So 7010 means, see this, 70 1 is nothing but all zeros will be present and 1 will be here, and all are zeros. Got it? And the next one is skip SNA means skip if accumulator is negative. So you have to test the accumulator, and if it is negative you have to skip it, and its instruction is 7008, so which means this part. Got it? And all the other things are 0. And the next one is SZA, skip if accumulator is 0, so which is taking 4 here, 7004, which means this one is 1 and all the remaining things are 0. And the next one is skip if E is 0, SZE, which means skip the next instruction if the flag E is 0. So we have E and you have to see it, and then you have to skip it, right? So which means this one is used. 7002 means this one, 7 is this, 00, and then 2 means this one. And next one is halt, 7001, 7001 means here. Now if you observe this, what has happened is, for the register type operation, this entire part has been fixed to something which will indicate that, oh, this is a register related operation, and now for every operation we are using 1 bit of this, right? Therefore, since we have 12 instructions, 12 bits here, we are able to have 12 types of register reference instructions. If you count them, they will be 12. 1 2 3 4 5 6 7 8 9 10 11 12, and each instruction is given 1 bit in the operand field. Alright, in case if this instruction would have been bigger, we would have had more number of instructions there. Okay, and the next one is input output related instructions. So for input output related instructions, so what happens is, this part is 7 only, but I part is 1. Therefore, all the input output related related instructions will have all ones in the starting 4 bits, which means this will always start with F. So if you look at this, all the instructions are starting with F. Got it? And now we are using F800. F800 means this part will be 1 and all the remaining parts will be 0. Right? And it is INP, which means input, get the input from the input register. So using this instruction, from the input register we get the word and load it into the our particular accumulator. And the next one is out F400. F400 means this one will be 0 and this one will be 1, right? So using this, what we do is we take the word from accumulator and we write it into the output register. Later that output register data will be read by some device like printer. So that is how we get the input into the CPU and we send out the output whenever we need using these two. And then SKI is, we are going to test the flag. There will be one flag for input and one flag for output. Why are these flags required is, sometimes, not sometimes, most of the times CPU will be faster and input output devices will be slower. Therefore, just to synchronize, which means a device will try to write into the input register, but it will take a lot of time. So during that time our CPU will be busy doing something else, and then after writing into the input register, the device is supposed to inform the CPU by setting a flag saying that I have written some input. For that one we are going to have a special flag. Let's call it as input flag, right? Input flag. Now this is saying that skip if input flag is 1, and this is saying that skip if output flag is 1. These flags are set for synchronization, right? And now this one is F200. So F is here, 2 is nothing but these two are 0 0 1 0, and skip if output flag is set. So this means F100. So 0 0 0 1. So this is F, this is 1. And the next one is IO on and IO off. So it is nothing but on the interrupts and off the interrupts. So interrupts we didn't discuss it, we'll discuss about them, and these two instructions are used to say that interrupts are allowed and interrupts are not allowed, and for them we are using F080. F080 means 0 0 0 0 here, and this bit will be set to 1 and all the remaining bits will be zeros, right? And here F040 means 0 0 0 0, and this bit will be 0 and next bit will be 0 and all the remaining bits will be 0. Now if you see this, in using this input output we have used the bits from 11 to 6. So 1 2 3 4 5 6. So we have used exactly 6 bits. That is why you can see that there are 6 different instructions, 1 2 3 4 5 6. Actually for this type of instructions also, which means for this IO instructions as well, we could have implemented 12, but we don't need 12 instructions. That is why we have used only 6 bits, but we have the capacity to extend it to 12 instructions because we have 12 bits here. Got it? So now try to understand this. Now using these 3 bits we can actually represent 8 instructions, 8 different instructions, but then we have used only 7 combinations to represent the types of memory related instructions, right? And for each instruction possible we have given 2 modes. Therefore 7 into 2, 14 instructions are possible, which are memory reference instructions. You can count them, right? 1 2 3 4 5 6 7 into 2, because this is depending on the mode we are getting 2 instructions. So 14 memory related instructions we are able to frame, and then if you fix all these 2 ones and this one to 0, we got register related instructions. And in that register related instructions, since we don't need the second operand, for every bit we are assigning one instruction. Therefore 12 different instructions we framed. So apart from those 14, 12 we framed. Got it? And then after that for the IO, again we have fixed all the bits to be ones, and using these 12 bits we could have framed 12 different IO instructions, but since we don't need those many, we want to keep it simple, we have used only 6 of it. In fact we could have extended to 12, but we have used only 6. Therefore we have gone for 6. So I think how many? 32 instructions are totally implemented, isn't it? So using a 4-bit opcode, only 16 are possible, but then we are able to use the remaining part and we are able to extend the number of instructions possible. We could have even extended it to 38, but then we don't need it, so we have extended till 32. Got it? And now you should understand, depending on the type of instruction it is, our actions will vary from here on. See, whatever the type of instruction it is, fetching is same, decoding is same, and after decoding, the next phase, if you remember, we have 4 phases in our computer, right? In our instruction cycle we have 4 phases. One is fetching, right? And the second one is decoding. So fetching and decoding are same, and the third one is getting the effective address. So that actually varies from type of instruction to type of instruction. In case if it is memory related instruction, you have to calculate effective address because you have to get the operand. And calculation of effective address is not required if effective address is directly given in the instruction, which means for these 7 instructions even though we need the effective address, we are not going to calculate it. It is directly available in the decoding phase itself, because in decoding phase the instruction part has that address and that address is already moved into address register. But then coming to these 7 instructions, we have to get the effective address into the address register. So for that we need one more memory cycle. In that memory cycle we are going to send the address which is present in address register to the memory as the address and get the word which is present in the memory at that address into the address register again. So it is funny, if you look at it, for these 7 instructions you might have to write something like this. From the memory you have to send whatever is present in the address register and get whatever is present there into address register. Why is this so? Because whatever is present in the memory at the address is nothing but the address for the operand, which is nothing but the effective address, isn't it? Therefore, for this part you have to calculate the effective address for these 7 instructions, and for these 7 instructions calculation of effective address is not required at all because it is already present. Got it? Now what does it mean? If you are spending T0, T1 for fetching the instruction and T2 for decoding the instruction, now T3 has to be, you need not do anything in T3 in case of these instructions. Whenever the instruction is given directly, address is given directly, and you have to get the address of the operand in T3 in this case. Therefore T3 is not used for these instructions, but T3 is used for these instructions. So T3, which is nothing but we are going to calculate the effective address, that particular phase is not required for this one, but it is required for this one. Got it? Only for memory related instructions. Now for the instructions which are not memory related, like these register reference instructions, once you have decoded the instruction you need not calculate the effective address at all. Therefore in T3 you can start execution. In T3 you can start the execution of the instruction, and if you can complete the execution in one cycle, sometimes you might require 2-3 cycles, but if you can complete it in one cycle in T3 itself, then at the end of T3 you have to again reset the counter, that sequence counter. Then what happens? T0 will start and the next instruction cycle will start. Got it? And in this case also in T3 you can start execution because you don't need anything from memory. Got it? So in this case T3 has to wait, you have to start the execution from T4, and in this case you can start the execution from T3, and here also you can start the execution from T3. Therefore different instructions will take different number of clocks in order to finish their execution. Got it? So once we finish, that is why instruction cycle will be different for different types of instructions. Now once an instruction cycle gets over, depending on whatever type of instruction it is, at the end of it that particular instruction has to make or has to clear the sequence counter, so that whatever cycles it has taken from T0 to T7 or T8 or T10, at that end after T10 or T7 it has to again go to T0. Got it? So how many clocks or how many timing signals should we have? We should have at least those many timing signals, as many as they are required by the longest instruction. If the longest instruction is going to take 15 clock cycles, then you are supposed to have from T0 to T14. If it is going to take 16 clock cycles, you are supposed to have from T0 to T15. In our case we have taken a sequence counter which is actually 4 bits, isn't it? So what do I mean by 4 bits? We can have T0 to T15, which means any instruction can take a maximum of 16 timing cycles, right? So after 16 it is not possible. So anyway we shall get into them, we'll understand it better. Okay, once I implement all of them we'll understand it better. I cannot give everything in a single go. Let's take one by one and we'll.
Hi, if you are planning to do masters, then doing masters abroad is better than doing masters in India. I'll give you all the reasons. So first reason is, out of 1 lakh students who take GATE every year, there are only 500 seats in old IITs. So all the IITs put together have an acceptance rate of 0.5%. and IITs, universities better than IITs, they have very good acceptance rate like 30%, 40%, but all the IITs put together have an acceptance rate of 0.5%. And if you are working hard to get into IIT Bombay's ranking is 177 and IIT Roorkee's ranking is 400. If you are happy to get into IIT Roorkee, then getting into universities better than IIT Roorkee is easier compared to getting into IIT Roorkee. And looking at the salaries for computer science, for software jobs, if you have done your masters in computer science in US, the salaries are ranging from 80 lakhs per year to 1.2 crore per year. So even if you take an average of 1 crore per year, your savings will be much higher than the salaries in India. After taxes and your cost of living, you can easily save 40 to 50 lakhs per year. And in India, the maximum jobs that you get is around 30 lakhs. So your savings will be much greater than the salaries in India. And these are all the services that we provide. University shortlisting. So depending on your profile, we will shortlist what are the universities that you have to apply, and statement of purpose building, and then LOR guidance, and GRE and English test assistance, and education loan assistance. So you don't have to have any collateral, which means without any security, now you can get education loan. Getting education loan is very simple these days, and whatever the amount of fee that you have a range of universities. You can apply for 10 lakh universities, 20 lakh universities, or 50 lakh universities. But whatever it is, you are going to get complete education loan, and you can pay off your education loan in 1 year after you get a job. And then we do visa assistance, mock visa interviews, and then connecting with the university alumni. So now you might ask why we should join Game of Visas. So the answer is we have 90% success rate, 99% success rate. And these are all the destinations that we guide the students to. So we guide students to any country that you want to go. So now it is not just USA. We guide to UK, Germany, Australia, Canada. So we guide students to all the countries. We work with all the destinations. And if you are interested in going abroad, you have to just drop us a message on this WhatsApp number 9494 555 454. Okay, thank you.